Greetings everyone. This is Pranav Vignesh. I'm here with my teammate Sumujit Bhattacharya to present the paper Learning to Act Without Actions as a part of our Advanced Learning Paradigms course seminar. So this paper was published in ICRA 2024 and it aims to encode actions for a reinforcement learning or reinforcement learning from into a latent space in order to make reinforcement learning more sample efficient. All of this will become more clearer as I explain the paper. So without any ado, let's get into the explanation. So this is just an overview. And here, let me first, as a preliminary, explain the reinforcement learning problem setting. So the reinforcement learning problem setting can be formally defined as a Markov decision process. So the Markov decision process formally consists of a tuple of like a state space, which is essentially the set of states an agent can be in. The agent here corresponds to like a computer, which can make a set of decisions, and the environment is everything else. And here we have a state space, which is a set of states the agent can find itself in. Then we have an action space, which is a set of actions that or the decisions that an agent can take. Then we have a transition dynamics, which is usually a set of probabilities which govern what is the next state that the agent will find itself in, given it takes a action at the current state. Then we have a reward function, which is a scalar value, which is given after each action, indicating how well the agent is doing. And lastly, we have a discount factor. So I'll explain what the discount factor is while explaining the objective of the Markov decision process. So I'll just quickly run over what happens in a single time step. So in a single time step, the agent receives a state and a reward. Then based on the current state it is in, it decides what action to take and it takes the action. This action goes to the environment, which then decides what is the next state the agent will be in and what is the reward that it receives for this. So the reward here indicates how well the agent is performing. So ideally, in the Markov decision process setting, we would like to maximize the cumulative sum of rewards that we receive. So ideally, we'd like to maximize summation of RT from 0 to infinity. But this formulation has a small problem. It is that the future is uncertain. So rewards at a given future are slightly less valuable than the current rewards. So as time goes on, the rewards become less and less valuable because they become less and less predictable. So in order to model this, we add a discount factor to this formulation where we seek to maximize discounted sum of rewards, which is the summation of gamma power t RT. So gamma is usually a value between 0 to 1, and as t increases, it decreases, bringing down the value of the rewards obtained at a later time step. So this is the reinforcement learning setting. Now, uh, let me go into some current difficulties that we face with respect to literature and reinforcement learning. So most of the reinforcement learning methods that we have today, that is the state of the art methods as of 2025, are extremely sample inefficient. That is, they require a large amount of interactions with the environment to learn effectively. So some reasons for this are that RL agents need to balance between exploration and exploitation. That is, they need to play around with the environment to realize what is the best way to do things. And at the same time, they also need to be able to like exploit the best, like the way of doing things that they've already discovered. So in terms of, you can think of it as like the dichotomy between going to your favorite restaurant versus trying something new out. So you would have to balance this. And ideally, if you want to find the best food that is out there, you would have to do a lot of exploration, which takes a lot of time, which here translates to a lot of samples. Other problem is sparse rewards. That is, usually rewards are only obtained, that is, large rewards are only obtained for some tasks. Like for instance, here it would be like after finishing your meal or something like that. So it is difficult to learn correspondences between other actions and this reward. For instance, it is in this example, you would also have to learn that going to a restaurant is part of the reason why you're getting satisfaction after you finish the meal. So it takes time for our legend to learn that. Then there is a problem of high dimensional state space and action spaces. So in most settings, the state space is high dimensional. That is, we receive usually like something like an image, input from multiple sensors, and things like this as the state. And action is also very large. We can take a multitude of actions. So to learn correspondences between a given state and an action, we would also need a lot of state action pairs due to the high dimension of this. So this is another reason for sample inefficiency. So as a comparison, here have uh, like some of the number of samples needed for like different state of the art methods. So we have like you can see even the most efficient methods roughly need like around 10,000 10,000 to 10 power 5 samples. So this is usually a prohibitively large number of samples in case you want to just do it completely in the real world. So this is one problem which RL faces. So this paper seeks to solve this problem uh, by like uh, using a technique which I'll explain in the next few slides. So one way you could think of solving this problem of like sample inefficiency is to learn from like unlabeled videos. So if you think about it, we have like millions of manipulation videos, millions of like in general tasks which you like to like our RL agents to do. For instance, we have millions of videos on YouTube with regards to cooking or assembly of a component or something like that. But one problem with this is that we don't have like action labels on this on these videos. For instance, imagine there's a cooking video. Don't really know. We just have a cooking video, and we don't really know what is the action that is being taken. That is, we don't have it in a mathematical in a vector form. Can see in the video that somebody's like pouring salt into a stove or something, but we don't really have like a vector representation for this apart from the frames. We also don't have more finer details like what is the force with which someone is holding the spoon, or what is the force with which someone is like squeezing a cup and things like that. So it would be necessary to learn these stuff as well if you want to apply RL to this problem. So is it possible to learn these additional details, these action labels from just video frames? This is a problem that uh, LAPO seeks to address. As a case study, consider MineRL. So MineRL is a competition that is held annually in which the participants are expected to code up an agent which can play Minecraft. So as you know, Minecraft is a very extensive game where we have a large number of actions that you can take at each step, and we also have like a large number of state spaces that you can be in. So on the right side, you can see an example. You can find yourself in like completely novel situations even after playing the games for hours to end, and you can take like multiple different actions. So it is an extremely hard problem to solve. And currently, we have like 60 million state action pairs which are provided to the players of the game. This is an extremely costly. This was an extremely costly process to obtain this. So it roughly costed around $250,000 to obtain this data. And even after this, the usually the results that are obtained for Minecraft are very subpar. It is not something which would be considered a good player in Minecraft. So one thing we have here is that we have a lot of streamer content for Minecraft. We have around 70,000 plus hours of Minecraft videos on YouTube. But a problem with this is that they have like zero action labels. That is, you just have often players playing the video game and very little information on what actions they are taking, what keys they are pressing, and so on. So one advantage of this is that it has like way more diverse environments than what is in the labeled data set. And it also has like another advantage with this is that it has like the latest versions of the game. If you are to label like state action pairs, then if you have like a particular data set, the game releases like a new update, then you'd find all of that a lot of the old updates to be like meaningless. Whereas here we can since there'll always be someone streaming Minecraft, you can always expect to find the latest version of the game to also be there. So so here is what LAPO seeks to do. So LAPO tries to essentially find out a method through which we can leverage this large quantity of unlabeled data for reinforcement learning that we find online, and use this kind of data without any manual annotation, and reduce the cost on like manual annotation. So if we could essentially do this, this would make RL very sample efficient, and this can like be a major advantage for like R&D research. So let me give you like a 30,000 feet view of like LAPO. So this is a very high level view. So here, LAPO essentially you can think of it as like having two stages. The first stage, we perform unsupervised learning on the unlabeled video set that I talked about. So here we just have the video of like somebody doing something or some expert doing something. And here our objective is to learn what are the actions possible, what action leads to what object, what outcome, and so on. And here essentially we try to learn like a latent space. So this is unsupervised learning part. Then in the second part, we essentially perform action mapping, where we try to map the latent actions with the that is the latent actions to true actions, and this enables us to like learn a policy. So, as per the authors of the paper, we can have like 1,000:1 ratio between the unlabeled and labeled data, and it will still work. So this essentially enables like web scale pre-training, which is essentially allows us to like just use like massive amounts of data that we have on the web to like pre-train our models, and this like significantly reduces annotation costs since the we have like a large corpus of data which can now be kind of like from which we can extract information. So let me go into the architecture. So here I'll first describe the architecture of the unsupervised unsupervised learning part. So this essentially consists of like two, two models. So first you have an inverse dynamic model, which essentially receives two things as input. So it initially receives the current state, or you can say the state before the current state and the state we are in as the input, and it seeks to produce latent ZT. So I'll tell what this ZT is when I explain the forward dynamics model. So in the forward dynamics model, we receive two inputs again. We receive the current state or current state, and then we receive the ZT. So using the ZT, our objective is to predict what the next state will be. So essentially, think of it this way: the inverse dynamics model receives how the world look like uh, before taking a particular action, and it also receives how the world looks like after taking that particular action. Based on this, it generates some information, which is then passed on to the forward dynamics model. So the forward dynamics model, using this information from the inverse dynamics model, along with how the world looked like before the action was taken, tries to predict what the world will look like after the action. So in some sense, you can say ZT kind of encodes the action. So if the inverse like sorry if the forward dynamics model is able to properly predict what the world look like after the particular action using ZT, then you can say it somewhat ZT somewhat represents the action. So here we use a technique called vector quantization to ensure that ZT is like present as like discrete interpretable clusters, which is like in line with what we expect action spaces to be. Uh, so then I'll like explain this in a little bit more detail. So as I said, the inverse dynamics model receives like two observations as input, which are usually consecutive, and then based on this, it produces a latent action, which is somewhat representative of the action, and and the forward this is and then this is possible the forward dynamics model. The forward dynamics model receives the current observation as well as the latent action. Based on this, it tries to predict the next observation, and it only has access to the world before the action was taken, and it needs to predict what the world will look like after the action has been taken. So here we train both of these together, and the loss that we seek to minimize is the reconstruction loss on the state predicted by the forward dynamics model. That is, we try to reduce the difference between what the forward dynamics model think the world will look like and what the world actually looks like after the action has been taken. So if we meaningfully reduce this, what this means is that the forward dynamics model with ZT and OT is able to guess what OT plus one will be. So this means that ZT is able to ZT is able to be a proper representation of the action which is taken to cause this change. And the ZT being a smaller vector forces compression. That is, it is not possible to just for the inverse dynamics model to just include like OT and OT plus one into uh, ZT itself. So this like forced compression allows us to like can be thought of as like the action which was taken. So here, as you can see, we don't really need any labeled examples. We just need like consecutive pairs of like observations, and from this we can like infer latent actions which caused this transfer. So this is essentially an overview of the unsupervised learning model. In order to understand what exactly this inverse dynamics and forward dynamics models are, you need to understand what vector quantized variational autoencoders are. So here I'll pass on the mic to my teammate Sumojit, who will explain the details of this.